think this is a problem which I given you as homework on yesterday. Try by using two-phase method. Okay. Was that correct?
Yes, sir.
Yes. Yeah. So how many artificial variables are there? How many artificial variables?
Sir, only one in the second equation, sir.
Yeah, only one over here. So your function like maximize z equals minus. Okay. So this is how normally we will write. So please don't confuse it. Don't confuse it with minimization problem. Okay. So whatever be the problem is, we will solve only as maximization. So maximize z equals minus a1. So a1 will be there in the there will be only one a1. So that is the auxiliary LPP. So phase 1 if you solve, okay. So phase 1 if you solve, okay. So the departing variable will be S1, am I right? So departing variable will be S1 and arriving or entering variable will be X2. Okay, and key number is, you can verify, key number is 1. Was that correct?
Yes, sir.
Yeah, iteration 1. So iteration 2, what happens is that, yeah, all Zj minus Cj minus Cj becomes either positive or 0. So that is basically end of phase 1. Okay. So but in this problem, okay, but in this case A1 exists in solution constant or product mix. So A1 exists in product mix. Yeah. So what to do? So what to do? So since all Zj minus Cj are positive, that means that an optimum solution has been reached. But artificial variables still exist in the product mix. So what to do? So you can stop the procedure. Okay. You can stop the procedure. That is, no need to proceed to phase 2. Stop the procedure saying that auxiliary LPP, okay, doesn't have auxiliary LPP doesn't have any feasible solution. Okay, doesn't have any feasible solution. Was that clear? Can you just upload your solution
Yes,
so
sir.
that others also can view it?
Yes, sir.
Okay, so whatever you did is correct. Whatever you did is correct. You cannot able to proceed to phase 2. The problem will terminate in phase 1 itself. Okay, you can write the conclusion as auxiliary LPP doesn't have any feasible solution. Okay, so these are some of the basic drawbacks which are there in the case of basically the simplex problem. Maybe due to many reasons, if you have not formulated properly, if you have not taken care of the problems properly, etc., these all things will happen. So I'll come to I'll just quickly, I will just go through that part. Okay. So yeah, so these all things we have seen in the yesterday's class. Okay. So some problems also we have seen. I'll just yeah, comparison of these all things we have discussed. So in the case of termination, you have to you have to think about alternate solution. Okay, unboundness, infeasibility, and cycling. So the present case is basically the infeasible solution. The whatever you have seen in the case of this two-phase one, it is an example of infeasibility. Okay, so it's an infeasible solution. Okay, now if we see the unboundness, okay, so if you try to plot this in a graph, okay, if you try to plot this in a graph, so taking this as x1 and this as x2, if you try to solve, so x1, if I put x1 as 0, I will get x2 as 6. So somewhere here I'll mark it as 6. Okay, so sorry. So x2 will be so 5 by 6. Value will be point something. Okay, so point something, and another value x1 will be 5. Okay, so your constraint will be something like this. This is the shape of your constraint, and since it is less than, so this will be your solution space. So next case is 3x1 is less than or equal to 15. Okay, so 3x1 is less than or equal to 15. So x1 value is 5. Okay, that this is how your constraint 1 looks like, and this is how your constraint 2 looks like. Okay, and the solution space is like this. Okay, now what can you conclude? What can you conclude? There is no, okay, there is no end. Yeah, there is no common feasible space. There is no common feasible space provided by both the constraint. Not possible to solve further. Okay, so that is not possible to solve further. Clear? So that is basically called unboundness. So if you solve the unboundness, okay, so you can see first I got the key column I found the replacement ratio I got. Okay, next thing when I perform, so S1 X1, now it is getting replaced. Okay, so you can see it is X2. Okay, but you can see over here, yeah, it is -6 and 0. Okay, so the replacement ratio will be 4 by 3 divided by -6, and this will be 11 by 3 divided by 0. Okay, so one is minus and other is infinite. So you can see to that it is not possible to proceed further. This is how an unboundness problem can be observed. So this type of problem, they are called unboundness. So if you plot it in by using graphically, you can able to observe it easily. Okay. So now the infeasibility already we have discussed, converted into standard form. I have gone for bigger method. Okay, so 3m plus 4, A1, got my first condition, went into the next condition. What happened? It is Cj minus Zj. Okay, it is now if I take Zj minus Cj, all becomes positive. Cj minus Zj is negative. All becomes either 0 as negative, but still artificial variable. exists in the problem. That in that case, the problem is infeasible. Okay, in that case, the problem becomes infeasible. So you have to ensure that whenever you are terminating, that artificial variable as should not be there in the solution space. It has to be removed off. If the artificial variable exists in your solution space, then your problem is infeasible one. However, you got a Zj minus Cj all as positive or zero. Okay, so these all are some of the assumptions we have followed in the LPP. So I'm not going to its detail. So I'll just move to the next topic, that is the primal dual conversion. What is it? The primal dual conversion is. Okay, basically this primal dual conversions. Whether primal dual is nothing but the dual is nothing but it is a mirror image of a problem. Okay, the actual problem given to you, okay, the actual problem given to you, it is called primal. Okay, so primal is nothing but your actual problem. Okay, the mirror image of your problem. Okay, the mirror image of actual problem, that is called dual. Either you solve primal or dual, it will end up in same answer. Okay, it will end up in same result. So what are the conditions to which you have to follow in the case of primal and dual? What are the cases in which, what are the steps in which you have to follow in the case of a primal and the book, whatever I am showing here is Taha. I think that you are able to view the book, view the screen. Am I right?
Sir, what's the book name, sir?
It is Operations Research by A.M. Taha. It's already there in your. It's already there given in your reference book. Okay, so you can see over here the objective function of primal if it is maximization. Okay, here it is given as maximization. If it is maximization, dual objective is of minimization. If your primal objective is minimization, your dual objective will be maximization. It is vice versa. Okay. If your constraint, okay, if your constraint, okay, is in the case of, okay, then when you are solving a dual, it will be vice versa. Okay. Or else you can see a maximization problem. Maximization problem will always have a constraint of greater than equal to. And a minimization problem, when you are converting into maximization, it will always have a constraint type of less than equal to. Okay, so this is the rule. This is a general rule have to follow in the case of primal dual conversion. Okay, if your primal problem is of maximization, dual will be minimization with a constraint greater than or equal to. If it is a minimization problem and in the case of dual, it will be of maximization with a constraint of less than equal to. Okay. Okay, right. Okay, is that clear? So we'll solve a problem. So you will get more idea in this regard. So I'm just writing a problem. So 8x1 plus 2. Okay, that is equals to maximize z. Okay, maximize z equals so maximize z equals 8x1 plus 4x2 subject to the constraints. Subject to the constraints 15x1 plus 8x2 less than or equal to 6. 25x1 plus 6x2 less than or equal to 840. x1 comma x2 greater than or equal to 0. So this is a given problem. So this is called as primal. Okay. So this is called as the primal problem. Now, how will you write how will you convert or how will you take its mirror image?
Negative into
How will you
objective
take?
function will minimize.
Okay, I'll come to it. Okay. So first thing you have to convert the problem into standard form. Okay. So the step one is to convert into uh, convert to standard LPP form. Okay. So what is standard LPP form here? That is inequality you have to convert into equality. Okay. Inequality you have to convert into equality. Can someone tell how the inequality will be converted into equality here?
Add with S1 or S1.
Yes. So I can rewrite this as maximize z equals 8x1 plus 4x2 plus 0s1 plus 0s2 subject to the constraints 15x1 plus 8x2 plus s1 plus 0s2 equals 650. Second constraint.
0 S2 comes there, sir.
Yeah,
It's just it
I'll
is
come
just
to it.
like okay.
I'll come to it. I'll come to it. 25x1 plus 6x2 plus 0s1 plus s2 equals 840. S2 is coming here in the second equation. Am I right? Hello? Hello? So S2 is
Yes, sir.
coming in the second equation. That's why I'm writing here as 0 S2. Okay. S2 and S1 is not coming. S1 basically it is value is 0. That's why we are ignoring in the in the second equation. Okay, so we are writing only S2, but when you prepare the simplex table, you are writing the coefficient of S1 as 0. So it means that basically this S1 is present in the second equation. Similarly, S2 is also present in the first equation. Okay, since the value of it is 0, we are omitting it. But when you write basically in the standard conditions, etc., it has to be there. Okay, clear? Was that clear? Okay, so now I'll write my the dual. Okay, now I'll go to write the dual. So as per the condition, what you have observed? As per the condition, what you have observed? So the dual objective. Okay, so dual objective will be minimize Z. Okay, minimize Z equals 650 y1 plus 840 y2. Okay, that is RHS side of my primal equation forms the objective function of the dual. Okay, then subject to. Okay. So the constraint formation will be something like this. So this set forms my first constraint. This forms my second constraint. So this is constraint 1, constraint 2. This is my constraint 3. This is my constraint 4, and this forms new RHS. Okay, these coefficient forms new RHS of the equation. Okay, so the first constraint, so I have two variables y1 and y2. So subject to first constraint, 15 y1 plus 25 y2, and the condition, what is the condition given? If it is a maximum, if the objective is, okay, maximization, objective is minimization, constraint type is greater than or equal to. Okay, constraint type is greater than or equal to. So 15y1 plus 25y2 greater than or equal to this will be the first RHS term. So will be equal to 8. Second constraint, 8y1 plus 6y2 greater than or equal to 4. Third constraint, yeah, so you have S1 and 0. So y1. So y1, okay, y1 greater than or equal to 0. Based on the next constraint, y2 greater than or equal to 0. Okay, so this conversion, this is called dual. Okay, once you got a dual problem, again apply the standard rules, standard procedures, etc., and you can solve. Okay, so first a primal problem I have converted into the standard LPP form. From the standard LPP form, you can see the RHS side of my constraint forms my dual objective. Okay, so how many constraints I have? that much variable will be there in my dual problem. Okay, so since this is constraint 1, so y1, this is constraint 2, y2. If I had one more constraint, it will be y3. So the number of variables, okay, number of variables is dependent on number of constraints in the primal problem. So this is my dual 650 y1 plus 840 y2. So the values are taken from here. So the x1 coefficients for the first two constraint, that forms my first constraint equation. This forms my second constraint equation. This forms my third constraint equation. This forms my fourth constraint equation. And you can see over here the decision variables are automatically getting converted into the condition of non-negative here. Okay, certain cases this will not happen. In that case, the whatever the variable which is not coming like that, you can say that it is unrestricted. So unrestricted in the sense means that variable can have a negative value also as acceptable. So that is what you can see over here. The variable size you can see it is unrestricted conditions is given over here. Okay. Here, is this clear? Is the step clear? Any doubt in this? Is the step clear?
Yes, sir.
Yeah. Okay. I'm just putting another question here for you to solve. So maximize z equals 5x1 plus 12x2 plus 4x3 subject to the constraints x1 plus 2x2 plus x3 less than or equal to 10, 2x1, sorry, 2x1 minus x2 plus 3x3 equals 8, x1 comma x2 comma x3 greater than or equal to 0. So this is your primal. Okay, get me the dual. Get me the dual. Yeah, please solve. Let me see. So first, convert into standard form. So standard form. So I will with the standard form. Maximize z equals 5x1 plus 12x2 plus 4x3 plus what will be the condition?
0 is 1.
0 s1. Anything to be added further?
No, no, no.
No. Okay, right. So subject to x1 plus 2x2 plus x3 plus S1 equals 10. Second constraint 2x1 minus x2 plus 3x3 plus 0s1 equals 8. Now convert into dual. So how many variables will come in the case of dual?
3 constraints.
How many variables will come in the case
Two,
of
two,
dual?
two. Y1, Y2. Two of them.
Y1, Y2. Okay.
So maximum is 10 by 1 plus 8 by 2.
Yeah.
The minimize, not maximize.
Yes. So it is minimize z equals 10 y1 plus 8 y2 subject to the constraints. Subject to the constraints. Tell
2
me.
y1 plus y2.
2y1.
2y1.
Why 2y1?
No, no.
What?
2y1 plus y2 greater than equal to 5.
First constraint I have only x1.
Yeah, x1
And
the
second is only
2y1.
2. So it is y1 plus 2y2. 2y2. Yeah. y1 plus 2y2 greater than or equal to 5. Okay. Second constraint
2y1 minus y2.
2y1 minus y2
Greater than
greater
equal
than or equal to
12.
12. Third constraint
y1 plus 3y2 greater than equal to 4.
y1 plus 3y2 greater than or equal to 4. Next constraint.
y1 comma y2 greater than equal
No,
to 0.
no, 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 no. I had only y1.
Only 3 constraints are there. There's s1 also, but we won't consider it.
Yeah, you have to consider. You have to consider this also as a fourth constraint. Previously also we have considered. Previously also we considered. You see over here, constraint number 1, constraint number 2, constraint number 3, constraint number 4. Okay. See here, this is 1. This is 3. And this is 4. Okay. So correspondingly, I will mark here 1. This is 2. This is 3. And this is 4. So same way here in this case, you will have only y1 greater than or equal to 0. That is y2 is unrestricted. Okay, so that's the way you have to write. So this is the dual. Is this clear? Any doubt in this?
One doubt, sir, that last equation, right? Last constraint.
Yes.
It become s1 y1 plus uh, 0 y2 is equal to greater than equal to 0 something we can.
Yeah, yes.
Then yeah, y1 greater
This
than equal to 0 will get.
y1 plus 0 y2 greater than or equal to 0. So 0 y2 I just removed off. So y1 greater than or equal to 0. So y2 is not y2. You can conclude that y2 is unrestricted. So y2 can take any value.
Okay, sir.
Yeah, any other doubts?
Sir, actually in that equation, no, sir. That is the question 2x1 minus x2 plus 3x3 equal to 8.
Yes.
Sir, actually, like I can't understand one thing. Like, what's the need to like actually add 0 s1, sir? But since it's already in equality form only.
Okay. See, S1 I am adding in the first constraint. Is that clear?
Yes, sir.
So there is no S1 present over here, but to show or but to take the terms properly, I have added 0 S1 here.
Oh, sir. Okay, sir. So
Got
then, sir,
it?
what if in the place of S1, if we put S2 also same result only will get, sir?
Which one? Which one?
In the place of S1. Hello, sir.
Yeah, yes.
In the place of S1, even if you put S2 also will get the same result only, sir.
You will get the same result. You will get the same result.
Okay, sir.
Any other doubts?
So here that artificial variable won't come, no sir. It will never
No,
come, right?
no need to take off the artificial variable in the primal dual conversion. Those are only about slack and surplus variable only.
So after conversion, then it
Artificial
is
variable
easier
will
to
come
do by
only in the
simplex
case of
method, right?
simplex problems. Simplex
Yes, sir.
problems to solve.
Sir,
Primal
one doubt,
problems
sir.
to solve. Yeah.
After converting to dual, we can
Yes.
normally solve it by simplex method, right? Then
Yes.
no need to consider artificial variable.
Again, now you can see all my constraints here are greater than symbol.
Yes, sir.
You have to, you
Oh,
have to again convert this into standard form. Okay.
okay.
Now this is a primal problem.
Okay, sir.
This is
Then
a
we should
dual
add A1,
into
A2 for
standard
considering
form is
simplex.
required whenever you are exactly all those things will comes into the picture.
Okay, sir.
Sir, in the previous problem, no, sir.
Yes.
Actually, you have given like y1 greater than 0 and y2 also greater than 0, sir.
Yeah, it is evolving over here. You see the first constraint. You see the problem. Both the constraints are less than symbol. So I added plus S1 here. I added plus S2 here. So when I written in the standard form, S1 is there in the equation number 1. So no S1 in the second equation. So 0 S1. And S2 is coming in the second equation. No S2 in the first equation. So I am getting here as y1 greater than or equal to 0. Here I am getting y2 greater than or equal to 0. Constraint number 4.
Yes, sir.
Clear?
Yes, sir. Clear.
Yeah.
So that's the reason like we are not actually adding that y2 greater than 0 in that next problem, sir. Since only one
Exactly.
S1 is available.
Exactly. I had only one. I had only one S1 here.
Oh, okay.
So S2 is not there. So why that's why I am writing y2 is unrestricted. I can show you some more problems also if you want. So I hope my screen is visible to you. You can see the example solved over here. I think that's all the same problem. 5x1. Yeah, 4x. The first problem I have solved to you. So the second problem you can see. Just as a look. So you can see over here, instead of writing S1, S2, etc., they will go with the exact variable dimension in the problem. Okay. So this is a foreign author book. So in all the foreign author book, they will not use S1, S2, X1, A1, A2, etc. They will all write in terms of X itself. So for to differentiate and for you to understand, we are going for these kinds of separate notations. You can. I hope you can see these things. certain problem, if you see over here, now in this problem, you can see x1 will becomes unrestricted. Okay, so that's the way the equation will change. And the mix-up results are also possible. See, you got here -5. So this constraint you are forced to change in the dual. So greater than, less than, all those things will comes into the picture together. So everywhere convert into the, you can see RHS is negative. So when RHS is negative, multiply, we have already seen. So this is how the equations are changing. Yeah, and okay. And I just want to show you one more thing over here. Yeah, so you can see in this graph. So this graph, so this is a particular problem. You can just note down. Maximize at equals 2x1 plus 4x2. Subject to the constraints x1 plus 2x2 less than or equal to 5, x1 plus x2 less than or equal to 4, x1, x2 greater than or equal to 0. So this is one particular problem. If you solve it simplex or graphically, you can see this point as well as this point, both are optimum basic solution. Okay, the point number B and point number C, when you plot it, ABCD forms your solution space where point B and point C both will becomes optimum. So that is called as alternative optima. Okay, alternate optima is present in the problem. So when alternate optima means more than one optimum point you can find in the solution space. Okay, that is, you can see over here. So x1 is 5 by 2, x2 is 3 by 2, value is 10. Alternate z value is also 10, where the x1 value is 1 and x1 value is 3. Okay, so if such a case exists, that is called alternate optima. Okay, so these all are the terminologies which comes in the simplex, unbounded, infeasible, okay, alternate optima, etc. So these are things, and degeneracy and primal dual. So that is the overview of your first module, that is the linear programming using graphical, solving by using simplex.